This is the recording that I mentioned earlier, which has a spontaneously firing muscle spindle, the positive going spikes, which you can see here in the blue trace. Where's my little cursor gone? And the spontaneous bursts of negative going spikes, which represent muscle sympathetic nerve activity, shown here. And the split screen feature of LabChart allows you just to peel back some of this activity, and you can change the time base. So let me just expand this. So here we've got the positive going spikes from the muscle spindle, and the negative going spikes down here, and the RMS processed nerve signal in the magenta below that. I've extracted the positive going spikes using the spike histogram and generated an instantaneous frequency plot in the trace above. Now if I just squash that back, so we can see this spontaneously firing muscle spindle shown here with a firing of about 20 Hertz. Before I go on to how we extract that data, it's worth just playing back using this feature in LabChart called Play Sound. So in commands, play selection of sound. So we can hear the spontaneously firing spindle, the burst of muscle sympathetic nerve activity coming in. So this can be useful when you're analyzing data, because sometimes it's much easier to hear a burst of muscle sympathetic nerve activity than to see it. So the audio playback is a very useful feature. That's present in both the Macintosh and the Windows versions. They're essentially identical, but there are different functionalities in the two systems. So I mentioned spike histogram. This is shown here. So we would first use spike train setup, and I'll just go new, and I'll call it muscle spindle. You can see I've already done this before. The data source is the nerve. I'll use the whole channel. We could select a bit if we wanted. The detector is what I want the level to be above the noise. So I may set it at 10. And it will find in this file 851 spikes. And then we go to Discriminator. And you can see there's a cluster of firing here, cluster of spikes, which you can see on the right channel. And down here, there's all the noise. So negative going spikes and just noise. So what we do is we bring these markers in. So we build up a, I just need to bring the lower one up. So we can just adjust these so we get basically this cluster of spikes. And then we can show in the Discriminator what this looks like. So this is what I've done previously, to call it units. So these are the standard spikes shown down in the lower trace, in this red trace here. Then we can convert these standard pulses into an instantaneous frequency profile using cyclic measurements. Yeah, so as I've done here. And you can see that when there's a little drop out in the spindle firing, there's a little drop in the instantaneous frequency, or if it hasn't captured one, we can just go through and adjust the overall discriminator thresholds to capture them all. Again, this is a complex recording because it's not just the muscle spindle, but there's also the muscle sympathetic nerve activity. This is useful because in this study we were applying galvanic vestibular stimulation. You can see in the orange trace here, and having extracted the MSNA by using the negative going spikes and having detected the positive going peaks of the GVS, the sinusoidal galvanic vestibular stimulation, shown here. So this is time 0, this is the first peak, the second peak, and you can see here using this cross correlation approach, we can identify that there is cyclic modulation of muscle sympathetic nerve activity. That is, there is vestibular modulation of muscle sympathetic nerve activity. Now, from this complex recording where we've got a positively going muscle spindle ending and a negatively going spikes of muscle sympathetic nerve activity, if you're interested just in MSNA and you consider that the spindle activity is a nuisance, well, you can see down here that just by using the RMS process signal down here, so this is RMS, similar to integral, we've got a moving average time constant. We can change that. 200 milliseconds is good, moving average. We can see that some of the baseline is in fact due to the spindle, of course, you know, that's generating quite a big signal, but we can still see that the bursts of muscle sympathetic nerve activity are clearly reflected in the bursts as shown in the RMS nerve histogram, RMS nerve signal rather. Now, I want to show you how we can measure that, and there's another very, very nice feature which you can see down here. I've labeled this green channel MSNA, and let me just show you what I've done here. I've again used cyclic measurements, and from the source channel RMS nerve, I'm just using the sine, so it can detect these sinusoidal events, and we can adjust the threshold, so we just get the events of interest. But what I've done, which is actually very, very nice, is use this feature, height. So rather than looking at all of these events, it will only look at those which have a certain amplitude, that is, from the baseline to the peak. And if I lower this, you can see that a value of 0.5 is picking up most of these sympathetic events, these bursts of nerve activity shown down here. So I'll just scroll along and you can see the RMS nerve signal. It's being detected here, it's being shown here, but the green trace is using, again, cyclic measurements to detect sinusoidal events that have a certain amplitude, and I've set the threshold as 0.5 millivolts. Depending on the quality of the recording, you may accept a much higher level or lower level, but again, this is working very well in a complex recording that features not just the bursts of muscle sympathetic nerve activity, but also positively going spikes from a spindle. And even this is useful if we've got EMG infiltration. We can just ignore that by concentrating on the negative going spikes. Now, another feature we can use also in cyclic measurements, we can look at, so I've shown you height, we could look at the rate at which these bursts are occurring. So we can just calculate bursts per minute, as you can see here, just in the same way as calculating heart rate, bursts per minute. Or we can get an overall count. So this is just the cumulative count. So as we scroll along, you can see this number changing. So this is a cumulative count. So the LabChart software actually has a lot that you can use to analyze MSNA or to analyze single unit recordings. And once you've set all your parameters up, you can use DataPad. Now, some of you will be familiar with this. If we just open it up, DataPad is like an Excel file. I'll just select all this and delete. But so the default for each of the columns here will be the mean value of each of the channels that has been recorded. But you can actually go in and you can change all this. So you can change it from the mean, for instance, the default, to say, for instance, selection information. So I want the start, and the next channel also want selection information. I want the end, and the next channel selection information. I want the duration. So we've now set these up, and then I may say, okay, I want from the channel RMS nerve, I want from peak parameters, I want the peak amplitude. And in the next channel, also from RMS nerve, also using peak parameters, I want the width at 90%. Sorry, at 10%. So that is the duration of the burst. And also from this channel, again using peak parameters, and I'll show you what I mean when I select that, I may want the rise time. And finally, I can get as many parameters as I want using peak parameters. I might want the peak area. So what do I mean by this? Well, peak parameters is found here. It's just a free download you add. Basically, you can set it up to display whatever you like. The baseline value and average of the first 100 milliseconds of the selection, you can change that. The lower threshold at 10%, upper threshold at 90%, etc. Basically, all of these features you can record, you can add to the DataPad. You get them all for free. I should reiterate that this is not the cleanest of recordings because of that spindle firing in the background, which is of course contributing to the baseline noise. It's not giving us a smooth baseline. Nevertheless, the peak parameters software is able to detect this burst and to measure the width and the height, the rise time, the fall time, the area, as you can see shown here. Now you can display that for all bursts. You could manually do this if you wanted. Let me just show you again what it looks like. You could measure all this manually Or you could set up a datapad to do what I've just shown, to specify from the channel that you want to record, RMS nerve, using peak parameters, the width, that is the duration, or in the next column, the rise time, or in the next column, the area. You can get all of these parameters, baseline, peak time, the time at the peak, the leading slope, the fall time, all of these, you could have them all lined up here. So the datapad is a very useful feature because it basically does the pre-processing for you. It does some analysis on the signal before you add it to the datapad. And this recording, I was primarily interested in recording from a muscle spindle, so I wasn't recording ECG or blood pressure. But if I had, then we could record heart rate, systolic pressure, diastolic pressure, what have you. We can add all these to the datapad. And then once you've selected an area, you could just go, let me just select an area, and you could just go add to datapad. Or you could automate it, and you could say multiple add to datapad. For instance, I want to select 1 second every second, and I could do that for the whole file, or I could just select an area shown here, and I can go multiple add to datapad. Every second, select 1 second every second, and just for the selection. As you can see, I can select the whole file, the block containing the selection, or just the current selection. I'll choose the latter. And so it's just now going through the file and adding all that data that I asked it to add to the datapad. And there you have it. You have all of these parameters defined, so the selection, start and end, and the duration, which we set at 1 second. The peak amplitude, etc. And then you can just export that. You can just save the datapad to an Excel file, for instance. Datapad as text. So you just save that and you'd export that to your analysis software. So I hope I've convinced you that the LabChart software and the freely available additional features such as peak parameters and place selection as sound, RMS or integral, and additional modules such as spike histogram increases the functionality of LabChart and allows you to undertake very detailed analyses of microneurography data, whether that be from single unit recordings of muscle spindle afferents or cutaneous afferents, or indeed multi-unit recordings or single unit recordings of muscle sympathetic nerve activity or skin sympathetic nerve activity. LabChart software provides a lot of functionality for your analysis needs.